first example of this kind of thin tail distribution. Second example is exponential distribution, and let's go over here. This is our exponential thing, and exponential distribution has a single parameter lambda, which is larger than 0. This is the probability density function of lambda exponent to the power of minus lambda x, and x positive, and the density function tails off exponentially again as x goes to infinity, and the distribution function is 1 minus exponent of minus lambda x, because the tail probability is like that, so the distribution function will be 1 minus that. Why so? Because we have to take the derivative from the probability from the distribution function to have the probability density function. So if we have our distribution function 1 minus e to the power of minus lambda x, and we take the derivative from that, we will end up with these values, lambda e to the power of minus lambda x. Alright, so the distribution has exponential tails, and will generally underestimate the probability of large claims. So we generally don't use a thin tail distribution because we are talking about claims, and claims might be large in size, in dollar value, so we have to model them somehow to be fat-tailed, and the probability of those large claims should be a little bit larger. Okay, so like in our normal distribution, the probability that the claim will be that amount is infinitely small, and all the claims will be actually concentrated here. If we talk about normal distribution, like 95% of the claims will be there, but fat tail distribution must be something like that, and has a very large fat tail. So exponential distribution again does not have that, and we can use the same kind of logic to place the probability and to place the sample for exponential distribution. So what we have here for our exponential distribution, we have the moment generating function of x, which is so we have 1 minus fraction of t and lambda. Okay, and this thing to the power of minus 1. Okay, so we have this equation where t is less than lambda, and from this equation we can find that expected value of x is 1 over lambda, and the variance of x is 1 over lambda squared. Note that the mean and the standard deviation are equal. The third and the fourth central moments and the coefficients of skewness and kurtosis we also considered in the further example. So our task is to simulate a sample of size n from exponential distribution, and we will follow the routine which we have already created. We just change that to sample exp for an exponent, and this is our exp. And for generating the function we are going to use the rexp. So inside we have to set the parameter. So let's say that we have generated with the parameter lambda which is 1, and this is our distribution. We can see that it is positive and it has slightly higher probabilities of obtaining values which lie beyond 2.5, which were the case of normal distribution. So let's just simulate a little bit more values, and we have these probabilities which goes maybe to 6 in this case. So let's zoom, and we have slightly higher probabilities of obtaining values up to maybe 6 or 7. Okay. Next point of interest is that we can simulate the sample of size n from the exponential distribution not only with this command rx, but we can use the uniform distribution to simulate the exponential distribution. How to do that? The method which actually is called solving u equals to fx for x, where u is an observation from a uniform distribution on 0.1, gives a result which can be implemented with the command x equals to minus, this is alternative way, x equals to minus log u over lambda. So this is the case for simulating x's using the uniform distribution. So how to generate a random sample of size n from this exponent of lambda? We have to use sample x1 will be minus log. Instead of u, we place the uniform distributed numbers with runif. Here we place n. Let's say this value is n, and we have sample log runif divided by lambda, and lambda will have a value of 1, like it was over here. So this value of 1. So n lambda and sample, and we have the sample large numeric, and we also are able to implement the same kind of transformations and obtain what we have to obtain. So like that. And here's our result, and it looks absolutely the same as it was over there. So the option for simulating random exponentially distributed random values with uniform distribution by just dividing by lambda and taking the logarithm of those distributed values from the interval of 0 to 1. Why we use exponential distribution? All in all, the flexibility of the exponential family as a model for data is restricted by the fact that it has only one parameter. But the exponential distribution possesses an important lack of memory property, which will be useful in certain reinsurance calculations. And the property states that for x more than 0 and w more than 0, the probability that x will be larger than x plus w, given that x larger than w, will have the probability that x more than x. So let's just write this property over here, property lack of memory probability that x larger than x plus w, given that x larger than w has the probability that x larger than x. So this kind of notation, x minus w given that x more than w, represents the random variable x minus w conditional on x, assuming a value greater than w. And we actually can express this lack of memory of property like x minus w, let's say like that, x minus w given that x larger than w is almost x, almost, with the triple equality sign, and we will consider this value not equal to, but has the same distribution as. Okay, so has the same distribution. The geometric distribution has an equivalent property in discrete time for an observed numbers of trials or claims, and it is a consequence of the independence of the trials involved. So this is the exponent distribution.